All right, thank you for coming. Thanks for that, Jim. Um, yeah, so I'm Tim. I'm one of the team leads here at Custom D, and we do custom software development, in case anybody was wondering. But also, we sort of started to experiment with generative AI. I've been playing around with it for a wee while now, sort of seeing what it can do, what we can get away with, how we can productize it, how we can use it reliably in people's systems. Um, and it's been a bit of a wild ride. This is me trying to keep up with everything that's going on in the generative AI world. Everything's changing, the names are changing, terminology is changing. You think something works one way one day, and then it's completely superseded by another approach the next day. So
this is like your kids' temple.
Yeah, full on, relentless. So I'll just do a little bit of a broad overview about how generative AI works. Just so we're all on the same page. So generative AI, it's a subset of the broader field of AI, but it's a system that creates new content, which can be sort of text or images or code, audio. And it does this by using models which are trained on sort of vast data sets, which it learns sort of patterns and data from, and then can sort of, from somebody's prompt, it can output something that people want in a sort of reasonably reliable way. And why do we want to add generative AI into products that we're building? Gives us a lot of opportunity to create sort of more advanced user experience for people, more personalization, dynamic content generating, so you can create content on the fly for someone specialized to what they're looking at and what they're interested in. But not only that, we can sort of do a lot more in the automation space. We can automate routine tasks. We can help people do better with less time. And also with problem support areas where everybody's got a big knowledge base of stuff in their company and nobody reads their internet pages, and we can make that stuff a lot easier to navigate and find and search. So how does generative AI work? I found a good GIF that sums this up. Magic. But under the hood, when you're putting in a prompt into ChatGPT, for example, that breaks it down into tokens. And these tokens are then sort of converted into token ID. So each ID there represents one of those tokens from the previous page. You'll see token 13 pop up a bunch of times because that kind of represents the full stop in that sentence. And anyway, those token IDs are then sent to your large language model, which is a neural network trained on transformer architecture. Don't ask me to get into that because it's way over my head. But anyway, token IDs come out and it spits out output token IDs, which, when you convert those back into the text, you get the output based on the prompt that went into it in the first place. And it does that sort of, it's actually surprising, works out, sort of does a reasonably coherent answer most of the time. And to get a good answer, you need to sort of put in a prompt to elicit the right response. So prompting is an art unto itself. You could do a whole talk on prompting, but to get good results, you need to get good at prompting. Asking the right thing and asking the right way is critical to get the right stuff out of it, particularly when you've got more complex questions or more complex data that you want to process. There's a few sort of techniques you can do to make them better. Like one we've found is, few shot examples where you give the LLM, here's an example of a question and here's an example of response that I like, and then ask it to answer another question, it will perform much better. And there's what a prompt might look like, where you have say you're making a customer support bot, comes up, you put in your product knowledge base, your company policies, the rules around how you want it to respond, the tone of voice it wants to use, any other things you need it to output. There's a bunch of ways you can control the prompt output that's coming out, like when you're dealing through the API. The main one is the temperature, which controls the creativity of the answer that you're getting. Like if you have a low temperature, those tokens come out in a probability-based order. So the lower the temperature, the less variability you're going to get in your answer. So the less creative it would be, I guess you could say. If you crank the temperature up, it'll get very creative to the point of incomprehensibility. So you can sort of temper that a little bit by adjusting top P and top K, which takes your top subset of possible words in the output. You've also got, you can control the amount of tokens you want back. If you want something with just a short answer, you can tell if I only want a short answer. Or you can say there's a specific top sequence I want to hit, and once you've executed those tokens, don't show any more. It can save you a bunch of money on tokens. Fine tuning is another way to improve model performance, where you sort of, it's like these models are pre-trained on vast data sets, but then you can do another layer of training on top. So you can say, here's some questions and answers that I have that I know are good answers, and they're answered in the way that I like. And you can do another training layer on that. For the most part, we haven't really used this approach for getting output. We've found that using the base models, we've got pretty good answers just through creating good prompts. Plus, you've also got possibly up to 33% higher inference fees when you're using a fine-tuned model, because there's extra compute involved there. And on cost, it's important to be aware of this. You know, NVIDIA's share price not gone sky high for no reason, so keeping tabs on how this stuff is charged is really important. So you charge per token. Input tokens are charged at a separate rate to output tokens. I think output tokens are slightly more, if I remember correctly. But there's a whole bunch of different models you can use. Some are cheaper, some are more expensive. Cheaper ones probably give you not as comprehensive answer, less intelligent models, less reasoning. But for your use case, it might be satisfactory for what you're trying to achieve. So no point paying for an expensive model when you could achieve the same result with a much cheaper one, particularly if you're deploying this stuff at scale. And just sort of as a sort of rough guideline to how much you're paying for things, this is a page of text. It's got approximately 840 tokens when I ran it through a tokenizer. So the cost to input that many tokens and get an equivalent amount of tokens out can vary between, you know, a fraction of a cent to like 7.5 cents. Right, vectors and embeddings, which is a key part of giving our applications a brain and understanding of the world. So vectors, it's a mathematical concept. So it's a way of sort of representing data. It's generally sort of expressed as a list of numbers. And they're pretty fundamental to how we develop AI systems. Once we get our data vectorized, we can then do stuff with it. So how might we sort of approach vectorizing things? So I took some of my favorite films, and then I've tried to sort of create a vector across a couple of dimensions. You know, you can say, I've got 2 dimensions here, action and comedy, go through and rate all of them, and then I can create a vector representing action and comedy for each of those movies. And then we can sort of start to plot them on 2-dimensional space, you know, comedy down the bottom, action up the side, and you can sort of see how those different movies relate to one another. But we've not really sort of captured quite enough nuance there. Like we've got Pirates of the Caribbean right next to Deadpool. So if we're making a recommendation system, you know, like my 8-year-old would really enjoy Pirates of the Caribbean, but I'm not sure I'd feel comfortable with him watching Deadpool just yet, although he would enjoy it. Right, so we need more dimensions, a lot more dimensions. And there's an AI talk, so we'll throw AI at the problem. And for that, we use embeddings. And embedding is a type of vector, but it captures semantic information. So what it does is, like, it can associate words and meanings within text with each other. So words like, you know, lion, cat, panther all might exist quite close together within vector space. So it captures that semantic relationship between words. And in many ways, it's similar to a large language model because it's a neural network, it's pre-trained, but instead of spitting out output tokens, it's spitting back vectors. And the vectors themselves, when they come back, they don't have a sort of, you know, a defined meaning like we saw before, like action and comedy. It's quite easy to understand what that means, but these have a sort of something the model has sort of determined and learned during training. You've got a whole bunch you can ask for a lot of different ranges of vector sizes. You can have sort of sparse vectors with maybe a few hundred different dimensions through to, I think some of the bigger OpenAI ones go up to 4,000 dimensions, which captures a lot of nuance, but obviously there's a computational impact somewhere down the chain. So how might that look? So I grabbed a database of movies, grabbed title and actors and, not actors, genres and whatnot, and I ran it through an embedding model, and we get an embedding that looks like this. So this is 1,536 floating point numbers ranging between 1 and -1, and they represent the model's understanding of that. Which is good, because now we have a mathematical representation of a thing. We can do maths on it. And the main sum you need to know, and I'm not going to get into the weeds with the maths because I'm not really a maths guy. But cosine similarity is the key thing to measure the semantic distance between different things. Once you've done this calculation, you'll get a number, which 1 will mean you've got two vectors that are identical, or 0, they're no similarity, or -1, which means they're completely opposite. And also you might see occasionally cosine distance used, which is 1 minus the cosine similarity, which will give you 0 being identical and 2 being opposite. Right, so we made a few sort of conceptual leaps here, but I guess the key takeaway through that bit was we can now match different things together and see how sort of semantically close they are. Don't worry about the math, because we can use vector databases. These are specialized databases that are optimized for processing vectors and running queries on those vectors. And they do them really sort of fast and efficiently, which makes it really great for running sort of searches. So you can search for two vectors that are close to each other across all your vectors, and that will happen quite quickly. So some of the stuff we've been playing around with, like we use Redis in production, had to play around with PyCone if you want to manage service. It's also got a good free tier if you wanted to play around. And also mucked around with Postgres with the PG vector extension on my local development. So how does that look? So say you've got my favorite movie, Pirates of the Caribbean. We can do a search on that vector against all the other vectors in the database and then rank them by similarity. So unsurprisingly, searching against that, you get all the other movies in the series are quite semantically close to them. You can see Pirates of the Caribbean Curse of the Black Pearl is exactly the same as Pirates of the Caribbean Curse of the Black Pearl, as one would expect. But then there's a whole bunch of other ones that are all sort of pirate, seafaring related things. Sinbad and Ghost Ship, and haven't seen them all. Well, what's interesting is you can also search by reverse ordering, so you can get things that are least similar. I had to put a budget constraint on this because there's some really obscure stuff I'd not heard of. But who's seen Mao's Last Dancer? Would you say it is not very much like Pirates of the Caribbean Curse of the Black Pearl? Good, it works. The system works. I watched a trailer of it. Yeah, it is nothing like Pirates of the Caribbean Curse of the Black Pearl. Or is Mona Lisa Smile is the other one. Who's seen Mona Lisa Smile? You've got some weird taste, mate.
Is it Julia Roberts?
Yeah, Julia Roberts. She's like a teacher in a 1940s boarding school or something. Yeah. But if you're building, like the example here is like you could build a good recommendation system like you see on Netflix. You know, if you've watched this, maybe these ones could be good. Obviously, you're going to watch some of the ones on this list. Yeah. But using that same approach, it also gives us quite a powerful way of creating search, which uses semantic meaning rather than lexical search, which is a lot more powerful. So we can do searches on a word like dog, but then it won't necessarily return stuff that mentions puppy or Great Danes or St. Bernards. Whereas a semantic search would understand that there is a similarity between that term and those words. And to do that, if you want to do that, you just take the user's search term, create an embedding of that, and then run and get that against all the embeddings in your database that you want to match on. So an example of that would be, just create one here, what do you want to watch? Invent a movie about pirates, and then it gives me all the movies I've got in my database that sort of semantically relate to that particular terms. So what sort of things can you embed? Embed all the things, some of the things you want to search on. So this can be like really powerful e-commerce solution if you want to create search or product recommendations like this product. This recommends other products based on the product descriptions and embeddings. You can look at customer feedback, embed it all, and then do a search on, what customers have said this type of thing, and then find all the customer feedback related to that. Anything else you want to process like that. Another important thing is tools and function calling. Now these terms are sort of interrelated, but I'll go through it. One of the problems with large language models is they've got no real sort of concept of what's going on in the real world. So I can say, so I have just tried this on ChatGPT recently, and they have plugged in a web browser, so it actually will give you a decent answer. But at the moment, Claude's got no sort of concept of the real world. So if you ask something like what the weather's doing tomorrow, it's got no idea. Or if you ask, what's the current share price of Amazon? No idea. You can't access your internal databases. Maybe you want to supply, sales data or customer feedback to it. No idea. And it also has a knowledge cutoff. Like this, Claude was trained up to, was it 2023? So if you ask it, who's running for the President of the United States, it still thinks Joe Biden's running at the moment. So the way you can sort of give it access to, what's that? That we know of. The way we can give our applications a sort of knowledge of the outside world is to use tools. And it's a broad term, but it's any sort of mechanism we allow large language models to have access to help answer a question. And that might be, you might want to call APIs or access storage, or maybe send an email or communicate with someone. Might want to reach out for a human. Anything that's sort of outside those sort of core capabilities you get out of the box. And to do that, we use function calling. Although I have noticed function calling and tool calling being used sort of interchangeably lately. But this is the process through which we allow the model to access functions and their outside world knowledge. And it's not a great term because the model itself is not calling these functions. What you're doing is you're describing, it's a data format structure almost. You're describing the functions you have available to it. It could use, how it calls them, and then it's you send that all through with a question. And if the model thinks it should call your tools to answer that question, it does that. And just to give you a bit of an example of how that would work, if we have a little function available that gets the stock ticker price of something, what we can do is we can create a description of that tool, which we can then send to the large language model. So we've got the name of it, what it does, what sort of data it's expecting to have passed into it, and the parameters of those data. And then when we ask the model a question, we can say, what is the current share price of Apple and Google? And the model will take that, look at the question, look at the tools it has available, and then it will reply back that it wants to use a tool. It wants to use the tool twice. One time it wants to pass in the ticker code for Apple, and the second time it wants to pass in the ticker code for Google. So you actually detect that and then run those functions at your end and pass back the results of the function calls to the large language model. So we've constructed these tool result objects, which is mapping those tool IDs to what was requested in the previous output. And then I just passed in the raw output from those APIs, which is just a free stock ticker API that I found online. And then you get back an actual answer from the API. So it's taken the information I've given, and then it's made a decent response. And we know that those current share prices, 222.50, was inaccurate. It hasn't just hallucinated that. That is based in reality. Right, the other term that you'll be hearing a bit is agents. And I quite like this description from Patrick Marlowe at Google. So an agent is an application that tries to achieve a goal by observing the world and acting on it using the tools it has at its disposal. So there's kind of, as I said, there's two kind of types of agent. There's like conversational agents that we're used to, like chatbots. You've all used ChatGPT, which is a basic agent, although limited tooling. It responds to a human prompt and provides all those personalized interactions. Then you've got a workflow agent, and that might be sort of triggered by an event or an action or something. You might be triggering it by a cron job. Maybe you want to process something every day and post an email to people, or you want to detect when something happens and do something on that. And they can operate quite autonomously. Maybe they do part of a job and then pass it on to a human. Maybe they can actually sort of do the whole job for a human without them even knowing about it or getting involved. So this is the sort of makeup of an agent, and there's like a million different ways to make an agent, but there's no sort of right or wrong way. I guess there's lots of libraries out there that will help you make agents and arrange the sort of interactions between them. But just do whatever makes logical sense for your applications. The key things is the reasoning loop, which is the prompt, which sort of explains how this agent is going to operate when an input or goal or task comes into it, all the tools it has to accomplish that goal, and a model which sort of sits there and does all your processing. So how do we sort of think about, how would I use an agent within my work to make my life easier? So I don't know how many of you have worked in an agency type environment, but this is a fairly common question I get asked, and I thought, it's always a bit of a pain putting all your time entries together, and this comes through.
But you do it with so little
I know.
complaint. Just none at all.
Well, you've got to sit there and you've got to think up an excuse, and procrastinate a little bit. It's very frustrating. So it wouldn't be good if I could get an AI agent to come up with the excuse for me, so I don't even need to be involved. So how do we think? And looked up, Slack's got an API, so I can tap into that. I created a bot and installed it on our company Slack. And then what it does is it calls a webhook when I'm @mentioned. So I've got a little Laravel application that sits there, and it asks, Anthropic, have I been asked for my time entries? Is an excuse needed? And if it does, it returns the excuse, and then I can ping that back via the Slack as myself. So, create an excuse without ever being involved, fully automated. It's beautiful. So then, yeah, it's a miracle, isn't it? So then I get, a nice excuse come up, and I get to procrastinate for a little bit longer.
The names here, of course, have been changed.
Yeah, completely. This is completely anonymized here. We're not here to point fingers. But that excuse is a little boring. That's the kind of the prompt I use. So I thought, we've got those parameters like temperature and top case. I thought it wouldn't be fun if change the prompt a bit and crank up the temperature, see if we can get creative. And now I can do really cool really cool answers. And this is a good one about me being kidnapped by aliens and readjusting to Earth gravity. This is brilliant. This is going to keep her off my back for a couple of hours at least. But I can tell what you're thinking. This is non-deterministic. There's a good chance we might give the same excuse again, and then she'll get suspicious and she'll be on to me. So luckily we can just change our architecture a little bit, because we've got the ability now to sort of semantically check if things are similar to each other. So we can just use our embedding models to create embeddings of the excuses we've used before, and then we can store them. And then when something new comes in, we can do a quick check. We can check that cosine distance to make sure our latest excuse is far enough away from all the other excuses so she doesn't cotton on. Anyway, agent workflows. This is a really cool area. We're still figuring this out, but this is a exciting space, because agents can use other agents as tools, which is really cool, because what you can do is now sort of create all these interesting design patterns and have different agents that interact in different ways. So you might have a bunch of sequential agents. Say if you're writing an essay or something, you might give the agent an initial goal, write an essay on this topic. And agent A might go away and might be your research agent. So you might say, analyze this topic, go away, do some internet searches to find, interesting materials of it, pull that all down and store that. Then you might have a secondary agent that comes along, processes all that information that your research agent has gathered up and created maybe a sort of summary outline report of your essay that you're trying to write. And then another one that could create a first draft. And then an important step is doing a reflection step and getting another agent to look at that report that you've written, analyze it and offer critique, and then do another cycle incorporating that critique. So that's an example of doing A, B, C, D in sequence. Another approach might be a sort of deferral, well, dispatcher type pattern where you pass it into a centralized agent that has knowledge of a whole bunch of other different agents, and it decides, like a signaling operator on the train station, which agent should handle that particular story, which agent has the particular tools and knowledge to process that particular task. Or the orchestrated one, which is a bit tricky to get your head around, but it's like you have one agent that has a whole bunch of different agents, and they all sort of talk and bounces back. Sorry, I ran out of time to do diagrams of these ones, but imagine you have a whole bunch of agents that sort of pass something between them in a way that sort of makes sense to them until they get a satisfactory result. Right, so RAG. So RAG stands for Retrieval-Augmented Generation. So it combines large language models with external knowledge retrieval. And this is another way of controlling, giving it outside knowledge from outside its training data, particularly if you want sort of specialized information and don't want the large language models to return weird stuff. I was talking to someone earlier about sort of eating rocks, because Google's recommended you do that occasionally. I found it in the Onion article and sort of thought that was the literal truth and served it up to a search request. 2 a day for the minerals. So how this works, so we store our knowledge base in a vector database, and then when a user does a query, do a search in that knowledge base and incorporate the information we've found related to that query into a prompt that goes back to the large language model to return to the user. So we get much better accuracy and relevance of our outputs, get less, hopefully no hallucination. Are we saying no hallucinations? We haven't seen a hallucination yet. Nobody's claimed it. And we can get sort of real-time knowledge updates without sort of retraining entire model. And we've got that sort of transparency, because once you know where the data's come from that it's telling you about, you can refer back to where it came from. So somebody, we've put this in front of a few people and they'll say, no, that information's wrong, but then we can actually say, actually, no, we can track the citation to that, and we can say it's referenced in the source material here. So how does it work? So say we've got our knowledge base. This is one section of our knowledge base. Do a parse over it and break it up into chunks. You notice the chunks are slightly overlapping, so we don't lose any sort of semantic meaning by having a hard break between chunks. Then each of those chunks are processed with the embedding model, and all the embeddings stored in the database. We'll have a ID back to the original document, the raw text of the chunk, the embedding, of course, and maybe some metadata. Then we have the query process. So our user comes along, asks the query. We pass in the user query, again pass back to the embedding model, create the embedding of the query, and then we use that embedding to do the cosine similarity search against a vector database of chunks. We can extract the chunks that we've identified as being semantically related to the query that came in, and then we feed in the user's original query along with the chunks for context into a prompt template, which then goes to the large language model and then back to our user. So a prompt template might look something like this. I just asked Claude, give me a prompt template to use in RAG, but you can see we've got our sort of system instructions that tells the agent how to behave. We have a slot where we can drop in all the chunked text that we've created and stored in our vector database that we've determined is relevant to the question being asked. We've got the original question asked by the user because we want the large language model to frame its response in a way that makes sense to the question that was originally asked. And then we've got some more instructions about how we want the output to work. In reality, there's a lot more sort of bits and pieces that go on in here to make sure we're sort of following style guides. There's a bunch of some of the companies we work with, they have a lot of acronyms they use which the large language model doesn't necessarily know or might think those acronyms relate to something else, so we've got to expressly define all that sort of stuff. Now that was a relatively simplistic chunking approach that I showed you before. It can get quite a lot more complex. So we went for the basic 6-sized approach, so you've just got a sliding window that sort of moves over all the pages in your knowledge base, sucking out the text and vectorizing it. But there's more sort of content-aware approaches you can do. So you can grab out, just particular sentences or recursive chunking to try and sort of match things back to bigger chunks. Or you can get the large language model itself to sort of study and work out what it thinks is a good chunk to put into the database. And you can use libraries like LangChain, have a lot of tools and plugins that can help to do all this sort of stuff and process documents. So agentic RAG, there's a lot of opportunities to use agents in this process, both in the ingestion stage, processing the knowledge base, and also when you're reviewing the user question. So one of the things we've got, as we're processing documents, we've got an agent that sort of reviews the documents and pulls out, titles and metadata and authors and publication date and all that stuff. So that can be stored in metadata. So when we do searches against that, we can use those metadata values to help sort of filter down what we're returning. But also when the user's asking the question, there's also, again, we've got an agent that does a classification of the question. We've got to avoid people doing prompt attacks. So we do a classification step to the large language model itself is quite good at sort of detecting if a piece of text has a prompt injection attack in it, which is when somebody's gone, forget all your previous instructions and do whatever I want you to do. It will detect that, and then we can classify that query as unsafe, and we won't send it into the rest of our system. But also as we've gone through, and once we have the answer back from the system, we can review that answer and see if it's a good one and say, has this answer, this is the information we've got, this is the question that was asked, this is the answer that was generated. Is it a good answer for that question? And then if it doesn't, can actually loop around and do another pass or reword the question. GraphRag. So this is a kind of new area. I'm not an expert in GraphRag, but this is a new way of expressing knowledge. Instead of the database structure that we saw before, you work with knowledge graph databases, which gives it a much more sort of holistic understanding of the context of something it's looking at. So you've got not just the data, but the relationship between bits of data. So say if you're doing a search for Spain, it will also have, understand there's a relationship between Spain and Europe and, Spain and the world, and also Spain and, the sites around Spain for a vacation thing. The Sagrada Familia's in Spain, or Park Güell. And then that allows, with the question, you can now start to traverse those graph nodes depending on what was asked. There are, you do get a much better answer using this approach. The disadvantages are it can be sort of slower and more LLM calls, and more context means more tokens.
More money.
More money from the video. So that's kind of this image of what a graph database might try and represent. It's got the Mona Lisa, it's painted by Leonardo da Vinci. This guy James likes it. He's visited the Louvre. So it can get depending on what's asked, you can start traversing those nodes, depending on whether those nodes sort of are relevant to the question that's been asked. Testing. So testing's quite involved. It's non-deterministic. You don't really know what it's going to answer, so it needs a whole lot of question, quite a lot of it manual, but it is able to test itself, which is somewhat handy. Particularly when you're tweaking, your prompt wording, those variables, you might be sort of adjusting the temperature or top K variables, try and get different results. Every time you do that, you're going to have to test it over a whole bunch of different questions to see that you haven't sort of mucked something up. So we do pass on internal testing, but also because we don't necessarily have the subject matter knowledge to be able to assess whether an answer is a good one or whether an organisation would give that answer to that question, we also work with their internal subject matter experts who do a pass over to check to make sure the results are appropriate. Then we probably roll out a restricted beta where you have some sort of friendly initial users who are encouraged to provide feedback. Like ChatGPT, or applications have the thumbs up, thumbs down, and feedback offering, so we can sort of track if we're giving bad answers. People let us know, and hopefully sort of why it was a bad answer, and then we can go and tweak things, adjust things. Sometimes they're asking a question that doesn't have the capability to answer because we haven't absorbed that part of the knowledge base yet. Bedrock. So AWS is not just a supplier of beer and pizza to meetup groups. They've got a platform called Bedrock, which is enables the building of generative AI applications on AWS. So a lot of these tools that we saw before, like the knowledge base, document storage, and access to those large language models in a secure way can be done through AWS. And they provide a unified API so you can access all that sort of stuff from your applications. And that makes it very easy to set up RAG applications and agents and stuff. I'm working my way through the AWS's AI Practitioner Foundation course at the moment. It's quite cool because I've actually been able to create my own tutor. Uploaded all the course materials into a knowledge base, and now I can just sort of chat to it and ask it about any sort of LLM type questions I have. All right. That's the end. Thank you very much for coming to my talk. Hope there's something of interest there for you. I know I touched on a lot of things there, so I've created a little web page of, if you want to find out a bit more in depth about any of those topics that I've done tonight, I've created a little web page there that you can find out some more about.
Thanks, Tim.